Howdy, it's time to start Lab 3, which is Sloss Sequences. This is such an important lab for you to do. At first glance, it may seem overwhelming, and my goal with this video guidance is to help you minimize the frustration and not have to guess at what I'm wanting. I have found over the years that students are really concerned about that issue. What does an instructor want? And sometimes they miss the mark of not seeing the big picture of how everything links together in the course content. You can't miss this link, not with Sloss, because it's too important to understanding what you're going to see throughout the semester regarding big sea level rises and falls known as transgressions and regressions. This is the Sloss Sequence map that's in your book, and you'll need to get your digital book and look at this diagram and download it. You can do a screenshot and use it, and it'll be essential for doing this lab. But it's not the only essential piece. You need lots of diagrams and figures throughout the book to do it. But I do want to take a moment to explain how to interpret these diagrams, because it is so important that you understand what it represents. So let's start by looking at this side called the Cordilleran, and this one, which is the Appalachian. I would tell you that the Cordilleran side of the continent of North America represents where we would see things like the Pacific Northwest today, Washington State, Oregon, Northern California, all of California, all the way down into the down here through Mexico, and then down here would be like the Yucatan Peninsula, where you have the Gulf of Mexico and Texas. On this side, which is the Appalachian, you're going to have the eastern seaboard. So that's going to be the Atlantic Ocean today. This would be the Pacific. This would be the Gulf of Mexico down here. So what does the middle section represent? It's the craton. So to define the craton, that's the actual landmass of a continent. When we talk about a shield of a continent, those are like the original least impacted sections of a continent from crustal deformation or deformation that occurs when you get plate collisions. Sometimes even plate tearing apart, which would be rift zones. But along both all three actually, the Cordilleran Mobile Belt, the Appalachian, the Ouachita is more towards the southern south part of the North American craton. We're just in the parts of West Texas, parts of Oklahoma, and even Arkansas. You would represent being smashed from down below, from the east and from the west. So as sea levels rise and fall, obviously we're going to have some inundation of an ocean that comes in from the east, if it's flooding from the east. Same thing from the west, from the Pacific side, and even from the south. Now, if you have mountains that have been uplifted, like you see these different blue sections that represent like the Antler, Orogeny, the Nevadan, the Laramide, so forth. And then you see over here the Taconic, the Acadian, the Alleghenian on the eastern seaboard or Appalachian Mobile Belt. Those are important because they can restrict how much water can flow into the middle of a continent. Now, let's take a look at that and kind of explain what the different colors, the white versus the brown in the middle means. Let me start with the white. And I'm going to show you one that's really easy to see, which is the Zuni sequence here and the Arb-Soroka sequence. At first glance, you might go, well, those were huge transgressions. And I'm not saying they weren't, because they were. But I tell you probably the most impressive one was this one called the Tippecanoe. You're like, well, it's not very big, the white in between. And you're right about that. But you have to take the white with the brown to kind of have a full story. So let me just use Arb-Soroka first. If the Arb-Soroka was in place, that means when sea level started to rise somewhere in the Pennsylvania and right here into the Permian and into parts of the Triassic, we had lots of ocean rocks that were laid down on the western margin, the Cordilleran margin, and also the eastern margin. notice that we had mountains on the eastern side, which was, I might add, the last time we had a major mountain building event in the Appalachian Mobile Belt. We had none over here. So we got more flooding in the Arb-Soroka of ocean water. And on either side of the east or west coast, you're going to have longer stretches of time that marine water from a transgression can flood the continent. Less time for it to stay in the middle because it's going to be working its way inward, right? The key is if you get real thick sequences of ocean rock in the middle of the continent, let's say Oklahoma, Nebraska, Kansas, South Dakota, those types of states, you're looking at a very unusual sea event that covered a majority, if not all, of North America. And that's why I've asked you to draw multiple different paleogeographic maps and label them, because you kind of have to get used to what sea level did in each time frame for the Sloss sequences to understand the significance of how that affects, for example, the evolution of dinosaurs and where we find their fossils. So to kind of link the two together, that's why it's important. So the bigger the brown blob, this is the news flash of the lab, the less of a time section we have of rocks from that sequence. So in the Arb-Soroka went from here and started to here. Well, if that's the case, we have a giant set of missing rocks in the middle of the continent for the Arb-Soroka. And so that means we likely got it laid down, or we didn't have the oceans there long enough to lay down anything substantial that could be preserved in the rock record. So when you're looking at the Arb-Soroka, compare it down here to Sauk, which is the absolutely largest of all of the unconformable contacts. And that's what these brown sections represent. So when you start looking at each one of these, you should see a theme. Tippecanoe had by far the smallest brown section, which essentially means that we had the least amount of unconformable contacts. How does that translate to understanding oceans? It means that we had total coverage, basically, of a Pyrrhic sea during that time. All right, so as I show you some examples from the questions that you're going to be asked to do, you might think it seems a little elementary at first to ask you to draw diagrams. I'm not saying this person did it right or wrong. For the most part, they did it right, and I love that they included the legend, but I'm going to show you two ways to do it, right? And you're like, well, how am I going to figure out how to get these in there? You can scan this with a scanning app and, hand write your answers in color, or you can just take out my diagrams, but don't delete my questions, and stick yours right on top of it. Just make them the same size. Either way works. But the point being is these figures like 10.4, 10.10, 11.9, 14.8, yeah, you're going to be going through lots of different parts of your book. And you'll see why, because it shows you the paleogeographic, which simply means ancient location of continents and how the ocean covered or did not cover the continents at that time. So lots of my prior students, especially those that have been on field course, said this is absolutely one of the most essential steps for them understanding Sloss sequences. Because once they saw it time period to time period to time period, and then we traveled to these places and saw it, they were like, wow, I get it now. I get it why we go to Sedona and there's oceanfront property of limestone, and then there's all this sandstone that wasn't even a beach line. It was something completely different, like a Sahara desert. So they began to understand the significance of that. So this is one student's approach to doing that. Here's another. You're like, wow, that looks so good. Well, this person was an artist. You don't have to be an artist to do this lab, right? But look at how effective this individual's ocean. They just drew water here and put waves to make it very clear. This was the transcontinental arch. They did not label that. It was part of the requirements. This would have been the Canadian Shield. So they needed to be labeling some of this as it asked you to do. Like they didn't label the Cretaceous and Interior Seaway here. They didn't label the Antler Highlands or Ancestral Rockies and Basin and Ouachita Mountains on this one. If you go back up to this person, they did. Okay, so you can see there's some good points to both, right? So as you move into questions 2, 3, and 4, you're going to need to use those to answer some of this. And some of these are common sense answers, like it may ask you, what is an Pyrrhic sea? What is a mobile belt? Well, you should know that by now. You get to question 4, it's asking you basically the locations of the different mobile belts. So you can't use this diagram, obviously, but you can do something similar to make that happen. When you get to questions 5 through 11, it's time to get busy using the Sloss Sequence diagram. And again, I've showed you kind of how to use it. Just as a refresher, this would be the western margin of the North American craton. This is the eastern margin. This is the southern margin. Everything in the middle would represent the middle of the craton. So what does that look like to us? Everything from the middle of Canada down to Mexico, straight down the middle. So you're looking at things like, Montana, North Dakota, South Dakota, Kansas, Nebraska, and I might add Texas. So all of those places are important as we're looking at this. So you're going to use those questions or diagram to answer these questions in detail. When you get to questions 12, 13, and 14, for whatever reason, this seems to be the hardest for students to conceptualize. So I'm going to make it really easy. So I just took it's a letter opener, but it also has a ruler here. And you just need to get a ruler of some sort. You can even use a ruler app on your phone if you want to. But you're going to measure in this section where it says craton all the way down for each of the 6 Sloss sequences. I am not saying this person did it right. Can you see this person put 17 centimeters for Tejas? That's how big they said this was in millimeters. And I'm not saying they said it was for the brown or for the white. Again, I'm not confirming or denying their answers. If I was measuring the Tejas, I'd measure from here to here. If I was doing Zuni, I'd measure the brown from here to here. If I was measuring Arb Soroka, I'd measure from here to here. If I was doing Kaskaskia, I'd move from here to here. Tippecanoe, the brown, from here to here, and Sauk from here to here. Subsequently, if you're measuring the white, you're looking at this section right here. And really, when you start to look at the Tejas, folks, there's really just 2 sides to it, here and here. So there's none. There's like no white in the middle at the craton because it didn't get flooded. For the Zuni, you would measure from here to here. For Arb Soroka, from here to here. Kaskaskia from here to here. Tippecanoe from here to here. And Sauk from here to here. And you're simply looking at the measurement of thickness of that section. When you get to questions 15 through 16, you're going to need to be able to use some of these paleogeographic maps. For example, this is one of them that you'll use. And if it asks you to take a look at these and then draw them, then do it and label them. For example, it might ask you to label the Cretaceous Interior Seaway. I might add, let's go a step further. This would be your shoreline. That would be really good information right here. And I would guarantee you that we would have found living animals of the Cretaceous period. So famous animals that lived back then, dinosaurs, in particular things like T-Rex and Triceratops. You can find their fossils, a lot of them in these regions. That's part of why I'm asking you to do this, is to have that concept of, okay, I get it now. I get why we find marine fossils all over Texas down here. And you would see things like Texas, Oklahoma, Kansas, Nebraska. But then you start getting into places like the Dakotas and Montana, and some of them are over here, some of them are over here. So you could find both marine fossils and terrestrial if you are in the right places. So that helps us know where to dig for these fossils, right? When you're doing 17, 18, and 19, you're going back to the thickness of either the unconformable contacts, which are the brown sections, meaning that's missing rock that's in the middle of the craton for these sequences, meaning the Sauk, Tippecanoe, Kaskaskia, Arb Soroka, Zuni, and Tejas. And if you're asked to talk about the white section, you're simply looking at the thickness of those sequences of marine rock that still exist, I might add, in the continent. That's what the white stuff represents. It represents we have rock layers from marine transgressions there. The thicker the rocks layers there, or the thicker your ruler measurements, that means the more extent we have of a rock record in those sections from marine transgressions. Doesn't mean it's all of it. We likely lost some to erosion. If we have very small ones like we do right here, then you're going to have a situation where we had a lot of erosion that took place before the next big transgressive sequence occurred. When you get to section 20 or question 20, it's going to ask you about one of the most famous transgressive sequences in North America. And it happened during the Cambrian period, and it's best seen in the Grand Canyon. As a matter of fact, it's right before the Great Unconformity. You're walking down either from the South Rim or North Rim, either one, and you get to the Cambrian Age rocks. You're going to be crossing over these three layers. The Mob limestone is the youngest of the three, the Bright Angel shales in the middle, and the Tapete sandstones at the bottom. So I'm asking you to interpret, what did the depositional environment look like for Tapete sandstone? So was it far away from a terrigenous input like making limestone? Was it the shoreline that made the sandstone? Was it the lagoon that made the shales and siltstones? That's what you're trying to find out. When we get to cyclothems in the late Paleozoic, you're going to learn how important they are. Let me give you the big picture reason why they are. They are evidence of ancient transgressions and regressions, but they also have some really cool stuff that we use called coal. So they generated a lot of fossil fuels. So what I'm wanting you to do is use this diagram to interpret, when we have coal, what kind of part of the transgression or regressive sequence was that, and where would we have made it? So we're not going to make it in the wide open ocean. Instead, we'll probably make it around here in the coal swamps, which would have been the edges of continents that partially flooded but didn't completely flood out. So as sea level went rise and fall, if it rose too much, it would bury the trees that would make the coal swamps and they would die. As sea level dropped, then we could have a swamp where trees could grow again, and we could get the sequence that went back and forth. When you get to questions 22, it's going to ask you to draw pictures again. And now I'm asking you to learn where the mountains were. Where were the mobile belts that were important? Because the mobile belts dictate how far inland a sea can transgress. And subsequently, it's also going to be boundary markers where we can actually get cyclothems where coal is. So for example, we certainly get coal that's indicative of certain places in the East Coast, for example, and during the Paleozoic. And even though these ask for Mesozoic, we get lots of them right in this section near Pennsylvania. And there's a reason for that. So that's part of your big picture understanding of this. As you get into questions 23 and 24, I'm not confirming this person did it right, but this is what the red box would look like. So you're taking a section and you're going to explain to me what that segment represents of each sea level 1, 2, and 3. This should look like a diagram you're familiar with from physical geology. So this person did not answer everything that would represent shoreline and nearshore rocks. They just said transgressions and regressions. I do believe they were pretty much on the right track for doing shoreline and nearshore rocks, and if they were doing a red box around the far away from terrigenous input, meaning your limestone and then your lagoon, they probably would have put the red box right in here. So that's it in a nutshell. And as you get started with this lab, this should really help you understand the big picture, because folks, you've got to understand how sea level relates to the development and evolution of life on our Earth, because it is directly correlated. And it kind of all started with, we had a big rise in sea level at the end of the Precambrian. Many geologists feel that was the melting of snowball Earth. There are other theories out there as well. So looking forward to doing this lab and getting it loaded up. Use a scanning app to make it one single PDF document instead of turning in 4 or 5 or 10 different diagrams. Just make it easy, simple. This lab will take you about 3 hours to complete, and I appreciate every minute that you spend on it. Thank you. Bye.